Alright, what's up guys? Hopefully you're going to be able to solve this nice and quick. Use this. I won't really worry about these sort of explaining your own words because I want you to do it in your own words, but I'll show you how to solve each of these. Alright, what is the velocity of an object that is 2.3 kilograms with 8.12 momentum? Well, we know that P equals mv. So we'll say, okay, 8.12 is equal to 2.3 times v. V is equal to 1.12 over 2.3. 8.12 divided by 2.3 equals 3.53 meters per second. What is the mass of an object with 24.22 p and velocity equal to 0.99? Again, p equals mv, so we'll just plug everything in. 24.22 is equal to m 0.99 divided by 0.99. M is equal to 24.22 divided by 0.99. 24.46 kilograms. All right. What is the P of an object with M equal to 22.98 and V equal to 7.43? .98 times 7.43. It's just that simple. And you can write either P here, or you can just write kilogram meters per second, whichever you prefer. It means the exact same. All right, a 600-ton train collides and connects with a 400-ton train at rest. The 600-ton train has a velocity equal to 10 meters per second. What is the final P and V of the collision? Cool. So let's find the final momentum, the initial momentum. Let's do 600 times 10, which is equal to 6,000 P. So if this is the beginning, then this is also the end, right? Conservation of momentum, it's PI. So then that means that 6,000 PF. Now, I know you guys are wondering about changing this to kilograms. You don't really need to because they're both in tons, right? 600 ton and 400 ton. And we can just leave it in this form. But if you wanted to change it into kilograms, you could. You would just have to look up the conversion. But you don't need to for this problem specifically. But for all the other problems, you should. What is the final V of the collision? Well, if we have 6,000 P in the beginning and then we have 6,000 P in the end, then we need to just write it like this. 6,000 is equal to the total mass, which is, instead of 600, it's now 1,000 times velocity divided by 1,000. 6,000 divided by 1,000 equals 6 meters per second. Hopefully that makes sense. Two bowling balls run into and bounce off of each other. The collision is perfectly elastic. Okay. A ball 1 has mass equal to 7.33 kilograms and velocity equal to 2.9 meters per second. Ball 2 has 6.89 and velocity equal to 3.44. What are the final velocities of the two balls? So the reason why perfectly elastic is important is because that means that the momentums of each ball are going to switch. So the momentum of ball 1 in the beginning is going to be the same as the momentum of ball 2 in the end, and the momentum of ball 2 in the beginning is going to be the same as the momentum of the ball 1 in the end. So let's figure that out. So B1, we'll say that P is equal to 7.33 times 2.9, which means a final initial momentum of 20, whoops, a little bit dyslexia there, 21.26 p. All right, and now ball 2, we'll say p is equal to 6.89 times 3.44. We know that that's equal to 23.70 p. Okay. So what's changing between the two balls? Is the mass changing of ball 1 ever? Is the mass changing of ball 2 ever? No, it's never changing. So the only thing that changes is the velocities. So to find the final velocity, we know ball 1 starts with 2.9, but to find the final velocity, we have to say, okay, ball 1 has a momentum now that's equal to 23.7 because it's perfectly elastic. So for ball 1, we're going to write it like this. We're going to say 23.7 is equal to 7.33 times velocity. Divide. That means our velocity is equal to 3.23 meters per second. Remember, for a perfectly elastic collision, right, you would just switch the momentums when you want to look at the final, right? So this becomes ball 1's final momentum, and this becomes ball 2's final momentum. So let's look at ball 2. I'll say, okay, 21.26 is equal to 6.89 times velocity. Divide by 6.89. V of ball 2, 21.26 divided by 6.89 is equal to 3.09 meters per second. All right, on to the next problem. At an intersection, 1,200 kilogram car traveling east 30 meters per second collides with a 1,500 kilogram vehicle traveling north at 25 meters per second as shown in the figure. Find the direction and magnitude of the velocity of the wreckage immediately after the collision, assuming the vehicles stick together. And if you hear something in the background, so at an intersection, a 1,200 kilogram car traveling east at 30 meters per second collides with a 1,500 vehicle traveling at 25 meters per second as shown in the figure below. So this is 30 meters per second, and that is 25. Find the direction and magnitude of the velocity of the wreckage, assuming the vehicles stick together. Okay, so first let's find the two different momentums. Let's find momentum of vehicle. We'll call that 1, and we'll call this one 2. So P equals mv, P1. So say, okay, mass is 1,200. Velocity is 30. Let's multiply this together. 30 times 1,200 equals an initial momentum of 3,600. All right, now let's look at this one. P2 is equal to M2V2, so that's equal to 1,500 times 25. $37,500. Okay, cool. So right off the bat, we know that this car going up has more momentum than this car going to left and right. So we know that it's going to be more than likely, if you think about it in like quadrants like this, right? If the collision happens right here at this center mark, there's this line that's 45 degrees, all right? If the object going left and right has more momentum than the object going up and down, it'll most likely land somewhere in this area right here, below the 45 degree angle. And if this object has more momentum going up and down than this one does have going left or right, then it'll most likely land in this area above the 45-degree angle. And if they both have the same, well, then that makes sense that they have a 45-degree angle going out. So this is what we're going to use. So right off the bat, we know that it's going to be above the 45-degree angle because the object going up and down has much more velocity than the object, or much more momentum than the object going left and right. So let's calculate the two. There's going to be an x momentum left and right and a y momentum left and right. Well, we already know that. That's here, right here, and right here. So we have 36,000 going in the x and 37,000 going in the y. Now, let's see, find the direction and magnitude of the velocity of the wreckage immediately after the collision, assuming the vehicles stick together. So, in the x direction beginning, we have 36,000, right? That's our momentum starting off, and we have to set it equal to the momentum afterwards. What's going to be the momentum after? Well, we're going to add these two together, right? They're now sticking together. So we have a 1,200 and a 1,500 vehicle sticking together. So I'm going to do that. 1,200 plus 1,500 equals 2,700. And we need that by some velocity v. So some velocity v, but remember this is only the x because we're using this x momentum. So this velocity in the x. Okay, so divided by 2,700, divided by 2,700. So 36,000 divided by 2,700 is equal to, we get a velocity in the x direction of 13.33 meters per second. Now let's look at the velocity in the y direction. All right, we only have this momentum starting out in the y, so we'll set that equal to it, 37,500, and the y is equal to 2,700, right? The two masses added together, and our velocity in the y at the very end. So let's divide by 2,700. So 37500 divided by 2,700 is equal to, we get a velocity in the y direction that's equal to 13.89 meters per second. So we have 13.33 meters per second going to the right and 13.89 meters per second going up. So let's draw this triangle right now. We have 13.33 and we have 13.89. So what we're really looking for is what's this value right there and what's this angle right here. How do we find this value? Well, a squared plus b squared equals c squared. So I'll label this side x, and we'll say, okay, 13.89 squared plus 13.33 squared is equal to x squared plus 13.33 squared equals, and now let's take square root of that, and we see that our resultant velocity, the velocity we have in this hypotenuse direction, we call that the resultant velocity, is equal to 19.25 meters per second. And I just squared these two, added them together, and then take the square root so we can find x by itself and so we can get our velocity. Right? And now we want to find the angle. Well, we can use whatever function we want to find this angle, but I'm going to use sine. So I'm going to say sine of theta is equal to 13.89 over 19.25. 13.89 divided by 19.25 equals, and then we're going to just take the inverse sine of this value right here. And look at that, we get an angle that is 46 degrees, which makes sense, right? Because we are just barely have more momentum in the y direction than we have in the x, so we knew it was going to be above the 45-degree angle, and so it lands in this area right here, just above 45 degrees, 46 degrees, and our resultant velocity is 19.25. All right. What is the change in momentum of a 0.16 kilogram pool ball that hits the sidewall at 0.4 meters per second and bounces back at negative 0.4 meters per second? The change in momentum. Well, we don't even have to do any math with this one. If we have some object, right, and it hits a wall at some velocity, let's write that 0.4, and it then comes back with 0.4, or in the negative direction, what's going to be that change? Well, to go from 0.4 to 0 is 0.4, and then to go from 0 to negative 0.4 is another 0.4. So really it's going to be these two like this. It's going to be 0.4 minus negative 0.4, which is a change in momentum that's equal to 0.8p. That's your change in momentum. What is the force applied to the ball if it made contact for only 0.1 seconds? Well, we remember that F delta T is equal to M delta V, which just stands for change in momentum. So we say, okay, F times 0.1 is equal to, we don't even need to worry about the mass, we can just say 0.8. To get the force, we just divide by 0.1. Say, okay, 0.8 divided by 0.1 equals a force, which means the force applied to the ball, again, messed that up, the force applied to the ball is equal to 8 newtons. All right. What is the impulse of an object that has 6 newtons of force applied to it for 8 seconds? Remember, impulse is just change in momentum, or just F delta T. So we'll write our impulse like this. 6 times 8. It's equal to 48. And that's in Newton seconds. Those are your units. What impulse must be applied to a 25 kilogram cart to cause a velocity change of 12 meters per second? What impulse must be applied to a 25 kilogram cart to cause a velocity change of 12 meters per second? We'll say, okay, 25. And the change in velocity is 12, is equal to J. Say, okay, 25 times 12, 300 Newton seconds. It's just that simple. All right, this problem looks long. That's because it is, but stick with me here. We can pick this apart. 65 kilogram ice skater moving forward with a velocity of 2.5 meters per second throws a 0.15 kilogram snowball forward with a velocity of 32 meters per second. Let's draw this. Ice skater. Those are my skates. Just awful. Snowball. Okay, what is the velocity of the ice skater after throwing the snowball if we can neglect any friction? Let's say that the flying snowball inelastically hits a second. Okay, let's pause right here then. Let's just look at this one. Okay, moving forward with a velocity of 2.5 meters per second, throws a 0.5 kilogram snowball forward with a velocity of 32 meters per second. What do we know about this problem right off the bat? If you're on ice and you're neglecting friction, okay, and really let's rewind this. What is the third law? What is Newton's third law? For every action, there's an equal and opposite reaction. That's what we're looking at with this question right here. We have two momentums that we're looking at. We have momentum 1, which is the momentum of the ice skater. So that's 65 times 2.5. 165 times 2.5, which is equal to 162.5 p. And then we had the momentum of the snowball, which is 0.15 times 32. And so really, when this snowball is released from this person's hand, it's almost as if the snowball actually hit the person with this weight in that velocity. And we treat it as such on a scenario like this, where an ice skater with no friction is throwing an object. And you can try this at home. If you find a way to get onto some sort of ice and you try and throw something, you'll actually push yourself backwards. If you start at rest, you'll push yourself backwards by throwing an object. It's really interesting. So what is the velocity of the ice skater after throwing the snowball? We'll just do it like this. It's really just 162.5 minus 4.8, right? Because it's hitting essentially with 4.8 p. So minus 4.8, which is equal to 157, again with the dyslexia, 157.7 p, and we'll set that equal to our object, our ice skater. 157 is equal to 65 multiplied by this velocity. We'll divide by 65, and we get our velocity is equal to 2.43 meters per second. Very good. Okay, the next question. Let's say that flying snowball inelastically hits a second skater who is initially at rest. Inelastically, which means it sticks. So let's draw that guy. And we'll say the snowball hits him right in the head. Boom, hits him right in the head. Inelastically hits a second skater who's initially at rest. The second skater catches the snowball. All right, I didn't read it far enough ahead, so he catches it, so it doesn't smack him in the head. This 60-kilogram skater is pushed backwards by this flying snowball. What is the skater's velocity after she catches it? Well, we'll say that the initial momentum of the system is equal to 4.8, right, because she has no rest, which means the final momentum of the system is going to also equal 4.8. So we'll say 4.8 is now equal to the total mass, right? So we'll say 60 kilograms plus the 0.15. So we'll say 60.15. And we'll say, what's that velocity? We'll divide by 60.15. And that velocity is going to be equal to 0.08 meters per second. All right, this last one, you guys have done this a million times, but we will do it together one last time. All right, so let's finish it up here. Well, so let me stop shaking that. Draw a large picture showing a car with mass 4,000 kilograms, another car with mass 1,500 kilograms. Car 1 collides with the velocity equal to 8.37. Car 2 is at rest. Car 2 flies off at an angle of 22.5 and a V equal to 5.98. Let's see, let's draw a large picture. Here we go. Car 1. Car 2. Car 2 goes off like this. And we'll say car 1, which is down here. We'll really say this. How about we do it like this? Car 2 goes off like that. car 1 goes off like that. There we go. That's our picture. All right. Initial P of the system, which is just since car 2, or oops, this should be a 1. Let's see, 4,000 times 8.37. That's the initial P of the system. So A. PI is equal to 33480. Right, P. Okay, letter B. What is the P of car 2? So car 2 flies off the velocity of 5.98. This angle right here, which is 22.5. So we're just going to multiply 5.98 times 1,500. So I'll do that up here. So 5.98 times 1,500. Right, just mass times velocity. That's going to be our P. 5.98 times 1,500. 8970. What is the momentum of car 2 in the x direction? All right, easy enough. We know that this has momentum of 33,480 here in the beginning, which means it has to have 33,480 in the x direction at the end. So let's see, to find the x direction, we're just going to do 5.98 times the cosine of 22.5. Or no, excuse me. Let me actually write our momentum in here. 8970. That is 8,287.2. The up and down is going to be the sine, so 8970 times 22.5 sine. So D is P2Y, which is equal to 3432.7. All right. P1Y, well, P1 is going to be the exact same as P2. 3432.7. That's just, there's no vertical momentum in the beginning, so that means that these two vertical momentums have to cancel out. So letter E, P1Y is equal to 3432.7. P1X, well, we know P1X just by knowing this number right here, because we have an initial horizontal momentum of 33,480. We need to have a final of 33,480. 8,287.2 of that is already taken away by car number 2, which leaves the rest for car number 1. So we just simply do 33480 minus 8287.2. That means that P1X is equal to 25,192.8. All right. What is the angle of car 1 after the collision? We're just going to do tangent. So I'm going to say tangent of over 25192.8. We're going to say, okay, the angle is then equal to the inverse tangent of that value right there. So let's find that. 3432 0.7 divided by 25192.8. 0.136. That means our angle 7.7 degrees. What is the P of car 1? All right, so now we need to just basically say, okay, if this angle is 7.7, then what's this resultant P right here? All right. So that resultant P is going to be something along, that's a degree sign, by the way. It should have been a lot smaller. So, I'll just use sine. So we'll say 343.2, 3,432.7, excuse me, holy cow, divided by 7.7 sine, enter. That means that we have a resultant momentum that's equal to 25,619.8 P. And then lastly, the velocity, we're just going to divide this by 4,000. And we get that our final velocity is equal to 6.4 meters per second. So that's how you'd solve that one. I hope you guys got all that on camera. If not, follow along to my voice. You guys should be very good at this problem though, because we've done it a million times. So good luck on the test. Let me know if you have any questions. See ya.